All right, hello everyone. In the last video I made about related rates, I accidentally made a mistake, or actually two mistakes on the last problem there. What I actually did in that problem was I solved for the rate at which the length of the person's shadow was changing, which is actually different from the rate at which the tip of the shadow is moving. So I want to kind of clarify this example. If you want to see an example where you talk about the rate at which the tip of the shadow is moving, I would go look at the video made by Dr. Knudsen where he goes over that. All right, so here's the setup again. A man who is 6 feet tall walks at a rate of 5 feet per second towards a street light that is 16 feet above the room. At what rate is the length of his shadow changing? So remember, this part is different from what Dr. Knudsen talked about in his video. All right, so let's go ahead and set this up here. So we have our street light, shining light up there. And this is 16 feet. And note, I'm going to be using a specific number for this because in the problem here, the street light isn't changing height at all. So I don't need to use a variable for this. All right, here is our person there. This person is 6 feet tall. And once again, I mean, they're not growing or shrinking as they're walking towards the light. So I don't need to use a variable for their height either. So what's happening is this light is casting a shadow on the person. So here's their shadow on the ground. And I'm going to call the length of the shadow L. So L is primarily what we're concerned with in this problem. And then I'm going to call the distance from the person to the lamppost. I'm going to call that X. Now, I do need to use variables for these because this person is walking towards the lamppost. So if we imagine what the scenario is in our head here, X is going to be changing as this person's walking, and L will probably change as well because the angle of the light different. Okay, so what we're trying to figure out here is we want to know the rate at which the length of the shadow is changing. So whenever we want to know a rate of change, that implies that we're really looking for a derivative. And since the length of our shadow is L, we're really looking for dl dt in this problem. Now, there is one more piece of information that we do know. We know what dx dt is. And this is where I made a mistake in the other video. This is actually going to be -5. Now, why will this be -5? It's because x is decreasing. And remember, when you have a variable that's decreasing, its derivative will be negative. So this should actually be -5. All right, so we have our picture and we have all of our information given. So let's go ahead and set up an equation for this scenario here. Now, just like in the last example, I'm going to be using similar triangles for this. So notice that we have two triangles going on here. We have this small triangle made by the man in his shadow, and then we have this larger triangle made by the lamppost and then the distance from the man to the lamppost and the shadow. So these triangles are similar. One is just a larger version of the other. So we can use the fact that similar triangles have the same ratio of side lengths. So when I construct the side length ratio for the bigger triangle, I'm going to do x plus L over 16. And then when I do so for the small triangle, I notice for the big one, I did the bottom side over the vertical side. So I'm going to do the same here, except only this is a length of L, and then this is a length of 6 here. All right. Next, what I'm going to do to make this a bit simpler is I'm going to multiply both sides by 48 because that's the least common multiple of these. So we can get rid of all the fractions. Multiply everything by 48. You could have also done this after you took the derivative. You could take the derivative at this point too if you want to, but I'm just going to clean this up before we do that. So 48 over 16 is 3. So we have 3x plus 3L is 8L. And so when we subtract here, we have that 3x is going to be 5L. So this is what we're going to end up having here. All right, so now we're interested in dl dt, so I guess I'm just going to isolate L. So we have 3x over 5 is going to be L right here. right, so with all of that said, let's go ahead and take the derivative of both sides here. So if I do the derivative, what are we going to end up with here? We're going to have, let's see, we're going to have the derivative here going to be 3/5 dx dt, and then over here we have dl dt. All right, so now we know what dx dt is. Dx dt was -5. So then that tells us when these 5's cancel that our shadow's length is changing at a rate of -3. This is what's happening with the shadow. So the shadow is shrinking at -3 feet per second. And this sort of makes sense physically. So the closer the man moves to the lamppost, the thinner the shadow is going to get because the light needs to come down at more an extreme angle. And then when you're right under the lamppost, the shadow will just be exactly where you are, meaning you really won't have a shadow at all. This shadow is shrinking into nothingness as the man walks towards the lamppost here. So this is the example that I intended to give for that previous video. If you want to watch an example where we talk about how fast the distance from here to here, or the tip of the shadow to the lamppost is changing, check out Dr. Knudson's. All right, I will see you guys in the video for lecture 19.